welcome to the Visual Studio 2013 launch, and I'd like to talk with you for a few minutes on new features in Visual C++ 2013. Now, there's a lot more than we can cover in 20 minutes. You'll find improvements in the IDE, in C++ AMP, and in many other places. But what I'd like to focus on is a recap of some of the features that we've added for ISO C++ conformance. Now, these are features that will help you as time goes on in any C++ compiler on any platform, and they really show how C++ code today is clean and safe and faster than ever because of these and other new features. So let's now review the new ISO C++ features in Visual C++ 2013. 11 new features that are in ISO C++ and now in Visual C++ 2013. And I've covered all of these before at the last two build talks, so this is a whirlwind overview where I'm going to show you code that you can look at length later, but to give you a taste of what the feature does, how it makes your code simpler and faster, and many of these are powerful features in ways that you might not expect. The first feature is explicit conversion operators. Now, the canonical example here is, what if you have a smart pointer type and you want to convert it so it's in a condition like if PTR at the bottom of the screen? In the past, we've had to have various workarounds that are so ugly, I'm not even going to describe them, that cause side effects like, oh, pointer times 42 happens to compile. This is one of those reasons why, even though it was a very small corner case, it still led to the reputation of C++ being complex. Well, now you'll be able to say explicit on a conversion operator, just like on a single argument constructor, so that you can say this operator should only fire in cases where I really do want a bool. I'm not just going to get a drive-by conversion to bool at the tip of a hat. And so the effect is that the green code works if PTR, and the red code does not work, just like you'd expect. And you're able to declare your intent to say, I want this conversion to fire only in explicit context. If I explicitly want a conversion to bool, which the if condition does, just like you could already do for many years on a single argument constructor. The second feature is raw string literals. Now, especially if you're doing work with XML and HTML, any kind of string encoding, directory and file paths, you'll appreciate how awful the bottom code was when you had to use backslashes to escape, make sure you had the right number of backslashes. Are you really sure you wanted 4 or 3 or 2? Now with raw string literals, what's in between the opening and close of the string is exactly what you type, including new lines, including backslashes. There's no escaping needed. And if you want to use the default characters that delimit the raw string literal, you can even change what the delimiter is so that you can write your raw string exactly as you want. This is very useful for everything from XML to SQL expressions, and you'll find this makes your code much cleaner when you have to deal with those kinds of strings to external libraries and devices. The third feature is function template default arguments. Now, in class templates, we've always been able to have default types for the template parameter type on a class. But we couldn't do it on function templates before C++ 11. Well, now we can. And that saves you some time when you might otherwise have to duplicate and overload the things that the templates you want to write. So for example, now we could write a container-based sort function, say, that defaults the functor type to less, the appropriate less for the container's value type. To get this effect in previous C++, you would have had to write the bottom code, which is to write your normal sort template just as we wrote it, but without the function template default argument. And then cut and paste your code to write the special case for less of t. Is it a big thing? No. But anything we can do to reduce code duplication, especially in headers, which affect compile times, and just to make our code cleaner, is a win. We're able to declare our templated code in a much simpler, natural, and straightforward way without needless duplication. The next feature is delegating constructors. Sometimes there's duplication in constructors because we have to initialize our member variables, and often we need to initialize them the same way, even in different ways of constructing the object, different constructor functions. Wouldn't it be nice if we could just take the common bits and merge them? Well, we've always done that. We've had a common init function when we've had lots of constructors and delegated to that. But that was really unsatisfactory for several reasons. In particular, you couldn't actually delegate the initialization of bases and members. You had to do something like default or otherwise initialize them and then assign to them or modify them in the body of the init function, which isn't really the same thing. And it adds an extra step that we'd like to avoid. If it's needless, we want to avoid extra work. This is C++ after all. So what we can do now in modern C++ is to have one constructor delegate to another. In the example here, you'll see that the second and third widget constructors delegate to the first constructor. And this lets us directly initialize name and data without first default initializing it, then assigning it. And you can even run other code after you've delegated to the constructor. For example, the third constructor delegates to the first one, but then comes back and additionally does extra work, like saying, by the way, I went and called the default constructor and output that to the cout. The next feature is uniform initialization. This is really an area where C++ is a lot cleaner and simpler and more predictable than it was before. If you remember the bad old days down at the bottom of the screen, the way that you initialize an object changed its syntax depending on what kind of object it was, what situation it was, and sometimes it was even ambiguous, like that first line in the second example, well, which was actually declaring a function if you tried to create an object using that syntax and then pass it default constructed temporary objects of some other type. That happened to look syntactically like a function declaration. And Scott Myers and others famously called that C++'s most vexing parse. Well, you no longer need to deal with all of those different things. In the top part, a single syntax covers all of these different cases of construction. There is no vexing parse because we're using braces. We can take a rectangle, a complex number, an array, and a type-safe container like vector and initialize them all the same way. Now remember, you used to be able to initialize an array with something like this nice syntax, but not vector. You had to default initialize it and go pushback. Really ugly. We don't want people to prefer arrays. There should not be a reason to prefer arrays because they're type unsafe. There are fewer and fewer reasons to resort to those. Use vector and use std array. You can initialize them just as simply now as any other type. And it's all consistent, easy to teach, easy to learn. The next feature that I know a lot of you have been asking about is non-static data member initializers. In particular, instead of writing the initial value of a member in a constructor meminit list, isn't it even better if you can just put that default value right on the data member directly? Now, instead of having to say the value in the constructor member initializer list, you can say it right on the data member itself. And that will get picked up instead of just the default constructor being picked up if you don't specify something else to construct that member with. Very clean and convenient, especially when you're specifying default values for commonly initialized members that are otherwise going to just default. You want to just default in many different constructors. Speaking of defaults, let's talk about this next feature of equals default. Sometimes you want the compiler-generated version of a function, but because of something else you've done in your class, you may have suppressed it. But really, the compiler-generated constructor, say, or assignment operator, would do you just fine. Instead of having to write it yourself by hand, you can now say equals default. And this is more than just a convenience feature. It is convenient, it's shorter and less redundant. But there are actually performance implications and semantic implications of doing this. First, the equals default implementation provided by your compiler might be faster in some cases than what you could write by hand. That's an important, attractive feature. If you want to have your type be a plain old data struct or a pod type that's bit copyable, writing your own user-defined special member functions can turn that off and make it not bit copyable safely. Whereas by saying equals default, you preserve podness if you haven't lost it in any other way, and you can write pod types and still get the benefit of writing the functions yourself, but saying I want the compiler to just provide the default implementation instead of suppressing it. So as an example, if I have a value type class that provides its own custom copying behavior, simply providing those first two functions would turn off the default constructor. But I say, no, I want the default constructor. I bring it back, but simply say equals default instead of actually writing it by hand. When you talk about equals default, there's a related but different feature that people often think about because it's very similar and you write it in the same place, and that is equals delete. Just like you sometimes may want to say equals default, give me the compiler-generated version of the function, sometimes you may want to say, hey, I don't want this function at all. So in a similar example here with class type, I'm restoring the suppressed default constructor like we showed last slide with equals default, but I'm saying I don't want to have this type be copyable. And so instead of just using the previous idiom of making them private and undefined functions that gives you a link time error in certain cases, compile time error most of the time, but a link time error in certain cases, now I get a simple and clear compile time diagnostic each time because I've been able to express my intent, say what I mean, and just say equals delete. I just don't want those functions, and they're suppressed and don't appear. Now, I showed this example because most of the time people think about equals delete on these special member functions to say turn off copying. But it's a broader feature than just that. What if you have an overload set and you want to eliminate an undesirable overload? So I can have a function bar that takes a long, so a large integer, but does not take a smaller one. I can require that in an API. This enables me to write APIs that are simpler and safer. Another example is, say I'm writing my own regex iterator. Regular expressions are a wonderful feature in C++11, and we've already been shipping those for a while. But let's say I want to define my own iterator over a regular expression. But when I create the iterator and I pass it a regular expression, what if somebody hands me a temporary object? Now, the iterator is going to store a pointer or a reference to that object. It would be a bad mistake to pass it a temporary, and then the iterator happily stores a dangling pointer or reference, which is going to blow up the next time you use the iterator. That's not as safe an API as we would like to write. But we can actually prevent taking an R value, a temporary object, using the technique showing here by simply overloading on an R value reference, which will absorb, in this case, a const ref absorbs all R values, equals delete that, so that if you try to call it with an R value, you'll select the second overload, and then the compiler will tell you, hey, it doesn't exist, and prevents you from making the mistake. But if you pass anything else, an L value, you happily take the first overload, and it just works. This is a nice example of an API that is easy to use correctly and hard to use incorrectly. That should be a design goal of all of our APIs. C++11 gives us the tools and deliver high quality, easy to use, but still screaming fast and efficient and flexible programs. The next feature is using aliases. You might think of these as typedefs on steroids because you can actually make them be templates, and they're more flexible than typedefs were. In fact, these are pretty much a superset of typedefs. And now that you have using aliases, you may well never write a typedef again. If you look at the C++98 code at the top, you'll see all places where you have to use workarounds if you wanted to get a templated typedef. For example, let's say I want to have a vector of t and my allocator, but I still want t to vary, so I'd like to templatize it. Well, since I can't make a typedef a template in old C++, I have to put it in a class, which I can make a template, and that sort of works, except that if I use it as a parameter, as in the third line, now I can't deduce the type anymore. I have to actually supply the type every time I call the function f. This isn't the greatest usability. If instead I use a using alias, I can make that a template in the bottom code. I can simply say, yeah, here's a vector of whatever type you give me, but bind the second parameter of vector to myalloc of t. Done, no fuss, no muss. It's just as easy to use in the simple case, and it works even better with less overhead in syntax, and especially without drawbacks in semantics for function parameters. It's deducible, and you can just use the function directly. A nice convenience feature that also delivers more power and better usability in modern C++. When you look at the draft C++14 standard, it actually makes use of this feature in new ways, and you'll find these in our product as well. They were just approved earlier this year in 2013, but we would like to thank Walter Brown for including them in the standard and our implementers for including them in our product, so that now you can actually make use of some of these very new, just added convenience features in the C++ standard library itself for things like remove reference, make unsign, and similar types, which now save you the need of having to write type name and colon type and the drawbacks in the function parameter list that we talked about, and just use the using aliases. That's new from C++ 14. We're happy to include that in this year's compiler. Finally, one very powerful feature is variadic templates. C++ has long been known for its power in being able to define generic code that is fast and flexible, and its templates are really still state-of-the-art and let you do things like the STL that still to this day cannot be done in any other major language that has generic features. What we've done here is taken that capability and made it even better. In particular, now you can write templates that have a variable number of arguments, and this is not like C varargs, which are type unsafe and icky and smelly. This is type safe. It is just as convenient as C varargs, but way better and safer, and don't lose any of the expressivity and performance of templates, but make them that much more powerful and usable. Once you put variadic templates together with some of the other features in C++ 11 that we already have shipped, which include move semantics and R-value references, that, as shown in the bottom of the slide, gives you perfect forwarding. So get used to this style. You may see it quite a bit in your own code if you're writing high-level libraries that pass through or adapters to low-level libraries. Here's a great idiom. Take a variable number of template arguments, which you then use to take a variable number of differently typed, potentially, function arguments, and then just use stood forward with the syntax shown here to pass them along. The nice thing about this is not only are the types accurate and you just pass them through, but even the R value or L valuedness, the temporary or namedness of the object, will get passed right through. Again, one of those features that makes C++ code screaming fast by avoiding paying extra overhead when you don't want to, and you can just forward what you get along to whoever is beneath you, the library that you're calling. One of the nice things of all of these different features is that they're very well integrated with each other in the ISO C++ language. For example, let's say we have this function template that's variadic. It takes a variable number of function template arguments. You can go ahead and have a vector of, say, boost any, a popular variant type, and use list initialization, and then go and instantiate that with a variable number of arguments and use auto, which we've already supported in the product previously, another new C++ 11 feature, to make my vector of that type, initialized in this flexible way. And here we've used several different features that just go together. You can use lambdas, async, together with variadic templates, and futures, range for, and initializer lists. All of these things work together. And that's one of the things that we enjoy so much about the way C++ is evolving, to make simple code simple with a few new features that work well together and fit and give you a nice way to express exactly what you want to say in an efficient way. We also have a few new features from another standard, from ISO C. So although our focus is on being a conforming C++ compiler, and we'll continue to deliver that until we achieve that fully and track the standard, we have had some customer requests for some ISO C features. So this is not saying that we're going to fully conform to ISO C as a standard. That's still not an explicit goal of ours. However, there are useful features that our customers really would benefit from. And so we've added 4. A couple of them are very small, just the _B bool, which is a Boolean type in C, and the ability to declare variables in the middle of a function. Together with those two basic things at the bottom of the screen, you'll see also compound literals. So the idea of being able to cast an initializer to a particular type and initialize that type, in this case pod mystruct, with that. These features are available when compiling in C mode. So you're compiling a C file or explicitly overriding saying compile in C mode. They're not available in C++, except the ones that already were, like declaring a variable in the middle of a block, which is also valid C++. But these let you write and use code that was written that uses new features in the C standard that have not yet been added to the C++ standard. And one other in that group is C99 designated initializers, where sometimes you just may want to initialize a particular member by name. And here are various situations where you might want to do that. This is fully supported, including, as the last line shows, for arrays. Again, this is in C mode. This is C code, not C++ code, but we support that as well. And that enables things like FFmpeg, which is a popular library and, among others, now compiles, runs, and is fully accepted in Visual Studio. I hope you've enjoyed this tour of some of the features that we've added. Remember, there's much more in the product, in the IDE, in C++ AMP, and in many other places. And as you know, in the months to come, we will be showing you additional ISO C++ features as this living language continues to evolve and be implemented across the industry, including right here in Visual C++.